Assalamualaikum and selamat sejahtera. In this topic, you will learn several types of basic semiconductor power switches and their characteristics. Before we discuss further, you must remember that all power switches can conduct current in one direction only. In this video, you will learn the voltage and current characteristics of ideal and practical power switches. We will focus on 4 conditions only: during off state or turn off, during on state or turn on, switching activity, and the requirement of gate signal. In all conditions, we will consider a basic circuit consisting of a power switch, voltage supply, and LED bulb. These two figures show the equivalent circuit of the power switch during the off state. The left circuit refers to an ideal power switch, and the right circuit is a practical power switch. In an ideal condition, the inner resistance of the power switch is infinite. Hence, we can consider the power switch to act as an open switch during turn off. Hence, no current can flow through it. However, practically, there is a small current that flows through the inner resistance. This current is called leakage current. Based on the circuit analysis, we can sketch the current waveform of the ideal and practical power switches as follows. To know the voltage characteristic, we need to apply KVL. Based on that, we can see that both the ideal and practical power switches have the same high voltage across them. The voltage is equal to the voltage supplied by the voltage sources. Thus, we can sketch the voltage waveforms as follows. According to the waveforms, we can describe the voltage and current or VI characteristics of both switches during the off state. For the ideal power switch, the device will block a large voltage with zero leakage current. Meanwhile, the practical switch will also block large voltage but with small leakage current. In summary, the primary function of the power switch during the off state is to block voltage supplied by the power source. Additionally, the product of current and voltage of the practical power switch will cause the device to generate power loss during the off state. This power loss is called the blocking state power loss. Next, let's see the equivalent circuit of the power switch during the on state. For an ideal switch, we can consider the inner resistance equals to 0. Thus, the power switch is equivalent to a short circuit and the voltage across it is 0. At this condition, the switch can conduct high current from the voltage source to the load. Instead, for a practical switch, We can measure the voltage across the power switch due to the inner resistance. The voltage is known as a voltage drop. However, in contrast to the off state, the inner resistance in this condition is very small. Therefore, the voltage drop is also small and it does not affect the operation of the power switch. Hence, the power switch still can conduct high current through it. According to the circuit analysis, we can say that the main function of the power switch during the on state is to conduct high current in electric circuits. Before we sketch the voltage and current waveforms, I need to explain another characteristic of the power switch. It is the switching characteristic that is referring to a condition when the power switch changes from the off state to the on state and vice versa. Keep in mind that the ideal switch changes alternately from the off state to the on state instantly. Thus, we can sketch the voltage and current waveforms like this. However, practically, the power switch requires considerable time to change from the off state to the on state and vice versa. Thus, it creates a time delay before the power switch can conduct maximum current during the on state and blocks maximum voltage during the off state. Additionally, the product of current and voltage during the on state causes the power switch to produce the forward conduction power loss. Meanwhile, the product of current and voltage during the switching activity generates the switching power loss.